Still representing the same situation. We had a function whose y derivative was 16, whose x derivative was 28 at a given point. So we can calculate for that function the normal vector. Now, if the slope in the y direction is 16, that means if we go over a distance equal to the j vector, 1 unit in this direction, we're going to have to go up 16 units in this direction. Of course, I'm still not drawing these things to scale. The z-scale is much compressed compared to the x and y scale, just so the pictures can be represented in a reasonable fashion. Similarly, the slope in the x direction is 28, so the vector I in the x direction plus 28k is going to represent the way the function changes if we move in the x direction. And these vectors will lie along our tangent plane. Now if we have a small interval, let's say this is a small interval that we represented previously, then we know that we have this rectangular box, and we know we have this, and we can draw the rest of this in here, and a parallel line here, and a sort of parallel line here, and so forth. And we can draw a section of the plane up here. I'm not going to attempt to do that. But that plane is going to be normal to the normal vector n, which is equal to the cross product of these. So let's say that's I plus 28k crossed with j plus 16k. That'll give us a vector perpendicular to this one and to this one. We already know the coordinates of this point. I think we said it was about 1.63270. Not a very good approximation, but we can get the coordinates of this point. Now we can get a normal vector, so we can write the equation of the plane. Let's go ahead and calculate the normal vector. It's I plus 28k crossed with j plus 16k. We could write this out in determinant form, but again, with only two components in each vector, we can do this rather directly. We're going to have I cross j. Now let's see, I is here, j is here, so I cross j is just k. And then we're going to have I cross 16k. Now I is here, k is here. If we do the right-hand rule, we find that I cross k is negative j. So we're going to have negative 16j. And then we're going to have 28k cross j. K is here, j is here. K cross j is in the negative x direction. That's going to be minus 28i. And k cross k is 0. So there it is. There's our cross product. Let's write it in the order ijk. We have negative 28i minus 16j plus k. Now you might compare this with your previous notes that tell you that this is going to be negative fxi minus fyj plus k. Also, we mentioned if we change all these signs, it's still a normal vector. It's still going to work. So we have a normal vector. We recall that our point was pi over 2, 3, 270, and 270 was not a very good approximation. From the point to xyz, I'll put the word from in here. From the point to xyz, the vector is what? It's going to be x minus pi over 2i plus y minus 3j plus, let's see if we can get this in, z minus 270k. Let's see if we can get the paper over here, we can see that. But what we're doing here is very straightforward. We're just taking the vector from the point to a point xyz, and xyz is on the plane if and only if then this vector from the point to xyz is perpendicular to the normal vector. So the condition is x minus pi over 2I plus y minus 3j plus z minus 270k dotted with negative 28I minus 16j plus k equals 0, and that's off the edge of the paper. Don't think you can see. Yeah, you can probably see the equals 0. And the dot product is easy. So that's negative 28 times x minus pi over 2 minus 16 times y minus 3 plus z minus 270 equals 0. We can distribute and so forth. I think we end up with something like negative 28x minus 16y plus z. And what are these numbers? That's going to be 48. This is going to be about 1.5 times 28, 43, 44. This is plus, that's plus. So 44 and 48 is about 92. These are both going to be positive. 270 is negative. So I'm going to say that's about minus 180 equals 0. Now you can check my arithmetic, but that would give us an equation of that plane. And remember, that plane we're talking about would be this plane here, this tilted roof above this floor here. Having calculated more or less accurately the equation of the tangent plane, what good is that? Well, if xy represents a point that's close in some sense to pi over 2, 3, then the slopes in the y and x directions will not have had much time or much distance over which to change. And this plane, if calculated accurately, would allow us to approximate f of xy equals z. Just plug the x and y coordinates into this, solve for z, and we see that if this is a correct approximation, we have z equals 28x plus 16y plus 180. Again, that's not accurate. Don't take that to the bank. You can calculate it accurately yourself by simply refining the calculations that you've seen here. This has taken our function, which was f of xy equal x squared y squared plus square root of y times sine of x, which is a very nonlinear function, and told us that in the neighborhood of pi over 2, 3, this linear approximation, this plane approximation, works pretty well and gives us a pretty good picture of the behavior of f of xy in that small region. As a little bonus, we've mentioned it already, so let's go ahead and calculate it. Let's find the angle between n and k. Remember that that was significant because the cosine of that angle is related to the ratio between the area of our region in the xy plane and our sloped region on the graph, lying directly above that region of the xy plane. So cosine theta n dot k over magnitude of n magnitude of k, just from the definition of the dot product. Now n was negative 28I minus 16J plus K. We dot that with K. We divide that by the magnitude of N, which is the square root of 28 squared plus 16 squared plus 1, multiplied by the magnitude of K, but K is a unit vector, so that's just 1. I guess we might as well write it in there, but we don't really need to. Okay, so what's that? Well, the dot product of this vector with K is just 1. This quantity down here, square root of 28 squared plus 16 squared plus 1, well, that's not a whole lot more than 28. 16 is about half of 28. I'm going to estimate that's maybe 33, approximately 0.03. What's this tell us? It tells us that, remember, the area of the upper region, the area of the graph, the area above our 0.1 by 0.05 rectangle is 0.005, which was the area of that rectangle, divided by the cosine of theta, which is about 0.005 divided by 0.03, and that's going to be about 30 times this, which is going to be about 0.15. Okay? Much greater area. About 30 times as great, because the reciprocal of 0.03 is about 30. Actually, the reciprocal of this would be 33, so it would be about 33 times the area of that rectangle. Why should it be so much? Well, because remember, 28 and 16 are pretty big slopes. That plane has a very large slope, so if we look at a little rectangle in the XY plane and look at the corresponding area, the area above this rectangle on that very steep plane, is going to be very much greater than the area of that rectangle. In this case, I'm estimating about 33 times as great.